What's up, guys? This is Shipmac. I just wanted to do a little bit of a deep dive on the engines on the BK117D2, which is the Hype Performance Group H145. So the engines are made by a French company called Safran, and as Safran does with their engines, they create the engines in a modular design, and that allows the mechanics to pull apart and replace the engine in separate modules. Now, the 2 Echo is a vast advance over the 1 Echo 2 that was in the BK117C2. We went away from VARTOMS, the variable rotor speed and torque matching system, which was bread and butter for those of us who knew how to adjust it properly, but it was an absolute bane of an existence for anybody who did not. So the mechanics who got good with that system became very valuable, and it would behoove anybody who was operating the C2 to keep somebody around and make sure they had somebody on staff who was really good with that VARTOM system. But now that we have FADEC, full authority digital electronic control, a computer now does all of that for us in fine detail, and it does an amazing job. So what I've got up right here is the modules that the 2 Echo is composed of. And so we'll start out down here. Module 1 is actually the output shaft, and this guy right here spins at a nominal 6,000 RPM. 6,000 RPM corresponds to 100% NR, which is 383 RPM of the main rotor system. Now, you guys notice there is still a variable rotor speed system in this, and at a hover it's 101. So I'll let somebody else do the math on that. I'm not going to quote a number here, but 6,000 RPM corresponds to 100% on your NR. All right, so coming up here, module 2 is the axial compressor. This is like your box fan, or like a turbo. This just, as it spins, there's blades that grab the air and push them straight back. All right. This module 2 is also responsible with this gear train right here for driving the accessories module. And that accessories module is what's going to run your alternator, which provides electrical power to the engine control units. It also provides the power takeoff for your starter generator. So the starter actually turns this at the beginning, and then once the starter is done starting, it becomes a generator, and this turns it. And then this also is going to turn your low pressure and high pressure fuel pumps, as well as your oil pump. All right, so moving on back, module 3 is your gas generator high pressure section. All right, so a turbine engine works the exact same way as a traditional engine. So on a normal engine, you got the intake, you got the compression, you got the power, and you got the exhaust. The difference between a turbine engine and a piston engine is, in a piston engine, that all takes place in the same place at different times. So as the piston moves down, it sucks in air. Then when the piston moves up, it squeezes the air. That air is squeezed in the same place that it was pulled in. Then you have the introduction of fuel and fire, and you have the power stroke, which takes place again in the exact same place. And then finally the piston comes back up, pushes that air out. The big difference in a turbine engine is you still have all of those suck, squeeze, bang, blow, but all of those 4 processes are happening simultaneously at different locations in the engine. So right here we have suck, right here we have squeeze, right here we have bang, and then back here we have blow. So we have intake, compression, power, exhaust. All right, and power takes place all throughout here, and technically from here on is exhaust. All right, so module 3 is your squeeze and bang all together. So after the air has been sucked in by this axial compressor, it flows across these stators, which straightens out the air. It's then pulled into this centrifugal compressor and slung outward at a very, very, very high speed. We've got the diffuser curl right here, which catches the air as it comes off of this. It's spinning. It catches that air and straightens it out and sends it straight up, and then curves it and sends it straight back. And then it fills this chamber right here. All right, this thing right here is called the diffuser curl, and the outlet of the diffuser curl is the highest point of pressure in a turbine engine. All right, so the air pressure right here is at the highest right now. All right, so we've taken the air, we've added mechanical energy to it and sped it up, right? And then we squeeze it through this area right here, which slows it down and builds pressure. All right, so you see this converging duct. It's sucked in by this and sped up again, and then here it slows down, which again we're trading speed for pressure. So kinetic and potential energy. This basket right here has a bunch of teeny little holes all over it where that air is going to flow in, the fire is going to burn, it's going to flow through this stator right here to straighten out that air. It's going to be very turbulent coming off of that fire. So this stator right here is going to straighten it out and get it ready to flow across this turbine at the optimal speed. This turbine right here, the only purpose for this turbine is to keep the fire going. So this turbine right here drives this shaft, which sucks the air in, compresses it, and feeds the fire. All right. It also, like we talked about, drives all of your accessories. So this turbine is sole responsibility is for maintaining the engine. Okay. 2/3 of the energy that is extracted from this fire is going to be used just to keep this fire going and to drive all the accessories. The remaining 1/3 will flow back into Module 4, the power turbine, where it will flow across this turbine, and this turbine is mechanically linked through a series of gears in the Mod 5, reduced down from its nominal speed in the low 40,000 RPMs down to the 6,000 that comes out. This guy right here spins in excess of 50,000 RPM at 100% N1. You guys are usually seeing 80 to 90% N1s, so you're not seeing quite that full-blown 50,000 RPM, but that's still an impressive speed for this to be spinning. All right, the air that flows through here also goes to the 1/3, 2/3 rules. So 1/3 of the air that flows through this engine is used for the fire. The other 2/3 is used for cooling and pressurization and all kinds of other stuff. All right, so we will move on to the next one. All right, and this is the engine completely put together, and you can kind of see everything going on here. All right, so we already talked about the axial compressor. We got our stator vanes here. What we didn't talk about is this guy right here. So this is the bleed valve. So when you've got your VMS page up and you've got those white and green diagonal line boxes in the top left and top right corners, those are called your bleed valve flags. So at startup, your bleed valve flag should be indicating, saying that this bleed valve is open. That means that some of the air that is pulled in by the axial compressor is not used, it's not sent by this at all. Or actually, it's pulled in by this, it's not used back here, okay? It is vented overboard. The engine does not use it, all right? So that bleed valve is open so that the engine only receives the air that it needs. But if the engine needs a high power demand, that bleed valve will close and extra air will be supplied back there to really ramp up the fire. But during engine start and for most of the operation in a D2, these bleed valves are going to be open. In a C2, you used to see these things close all the time. You pick it up to hover, they'd flicker open and closed, open and closed. But as soon as you pulled that thing up and started doing anything at all, those bleed valves were closed. I have not yet seen a bleed valve close in flight on the 2 Echo engine. It produces so much power, or it's capable of producing so much power, that in operation on the H145, this engine is not even breaking a sweat. So those bleed valves stay open. If there's some other operators, some people who have some experience in high, hot, and heavy situations where they may actually see this thing close, I'd love to hear what it actually takes it to close. But I've never personally seen that bleed valve close on the 2 Echo engine. All right. Um, Another thing we didn't talk about is this thing right here. So this is the main fuel injection, and this engine uses something extremely interesting and different than any other turbine engine that I've ever worked on. All right. Most turbine engines use sprayers. So they atomize and spray in a cone shaped spray, and you'll have multiple of them around the engine. So, like right now, we're looking at a 2D cutaway of the engine. If you were to turn and look down the front of that engine to where you're looking at a circle, you would see um, injectors all along this portion here of the engine. And that's where the fuel is sprayed into this fire and feeds the fire. This aircraft, they pump fuel down through inside of this shaft and into this component right here, which has little holes all along the outside of it. All right, this is called the slinger wheel, the main fuel injection. All right, as this thing spins at 50,000 RPM, it just slings the fuel out into the combustion chamber. It's really amazing. It's so simple, absolutely simple. You don't have to worry about your injectors getting clogged or having a weird spray pattern. Big old gaping holes in this thing, and as long as that thing's spinning, you've got fuel being injected into the combustion chamber. So it's really cool. All right, you'll notice right here the forward section, so your high pressure section, is not mechanically linked to your power turbine. This is your N1. So when you guys see N1 on the screen, on the VMS page, that is the speed of this. Your N2 on your triple tack is the speed of this gear train. They are not mechanically linked. So the engine can only control this. Whoops. The engine cannot physically control this at all. This is a natural consequence of this. So, if the engine or if the aircraft says, hey, I need more power, you're not giving me enough power, my rotors are slowing down. I want my rotors at 101, they're at 100 flat, give me some more power. The engine will supply more fuel to this slinger wheel. That fuel will create a bigger fire, which drives this faster, which pushes more air through, and then that fire and that air, after it flows through this, will push that and speed that up and provide more power to the main rotor system. So the engine can only control your N1. The engine absolutely cannot control in any way, shape, or form the N2 directly. It uses the N1 to push the N2. All right, so here is the entire cycle as it happens. All right, so as the air comes in, here you have T1. So the air velocity comes in, and there it is. So just kind of imagine this right here coming up. So it slows down as soon as it exits the axial compressor. All right, and that should be velocity. That looks weird. Yep, that's right. So it slows down, it comes through, and now we're going to slow it down again, which is why you'll notice every time this velocity goes down, the pressure goes up. And then we're going to add more energy right in here and immediately slow it down. And then right in here, as the air drops into this combustion chamber, the pressure drops slightly. So remember where I said the outlet of the diffuser curl is the highest point of pressure, which is right here. All right. The other thing you'll notice is this number 3. That is a very significant number. We call that P3, pressure 3. That's this tapping right here. All right. We're going to use that air later on to do some things. We use it to pressurize our seals in the engine. We use that to clear out the start fuel. We also use that for cabin heating. So when you turn the heater on in the cabin, it's taking this air right here and dumping it into the cabin. And that's what's used for heat. Now, it is not using the fire. At this point, all we're doing is compressing the air, and that air heats up quite a bit. So, right here, we're showing outside air temperature is 15 degrees. So air is sucking in at 15 degrees. As you pressurize this air right in here by slowing it down in these divergent ducts, or these convergent ducts, as the pressure goes up, temperature goes up. All right? Until right here. Now, pressure and temperature are no longer linked together, all right? Because now this is the fire. So the pressure is still decreasing inside of this combustion chamber, but the velocity is increasing. So as that fire burns, that air starts moving back extremely fast under constant pressure, relatively constant pressure, and the fire spikes up. So you'll notice right here, 307 degrees Celsius is the outlet of this diffuser curl. So that is some extremely hot air coming out of this diffuser curl. That air is diluted down with cold air coming from outside the aircraft where it's pumped into the cabin, by the way. So right here, when this thing is running at 100%, cranking wide open, then you see right here 4,500 degrees Fahrenheit, 2,500 degrees Celsius. That fire is burning. Now, there's not a substance known to man that is going to withstand that fire without breaking down. So what they actually do is there's lots of little holes coming through this thing at a very, 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 very shallow angle to the material. You've got large holes where the air flows in to feed the fire. This is your primary air coming in, so it surrounds, it flows through the inside of those stators, so those stators are hollow. It flows through those stators, and there's actually teeny little holes on the leading edge of those stators as well. Highest point of pressure again, surrounding all of this, so that air pumps out through those teeny little holes, gets blown back by the fire, and actually surrounds this stator with a thin cushion of relatively cool air. Again, we say relatively cool air because remember, that air outside of there is almost 600 degrees. But compared to 4,500 degrees Fahrenheit, that's pretty cool. All right, so same thing with this combustion liner. All along here, there's lots of teeny little holes that the air blows out of, and then as the fire hits that air, it curls over and rides right along that and provides a thin cushion of air so that the fire doesn't hit it. All right, continues on back. Now we're going to keep it at a fairly constant temperature. I say fairly constant temperature because right now we are trading pressure for velocity. All right, so pressure is going to drop very quickly as it comes through here. You notice we have a divergent duct. Dang it. All right, there's a divergent duct right there, meaning we got to fit all this air through a very tight passage, which means that air speeds up a whole lot. As air speeds up, the pressure drops. All right, Bernoulli's theorem. as that air flows across that power turbine, it spins it. All right? So we're using that pressure drop to continuously drive that faster and faster and faster, and we're extracting a little bit of the energy from that as we do it. So instead of slowing down the air, instead of slowing down the air, we're speeding it up, and then we're extracting the energy out of heat and pressure. All right, it continues to flow through here in constant pressure, constant temperature, and constant speed until it goes through another set of stators to smooth out the air, because as the air comes off of this, it's going to be spinning, because again, that thing is spinning at 52,000 RPM. All right, as it flows through that stator, we have another I hate convergent and divergent. We have a passageway that's getting bigger, so the air is going to drop in pressure. All right, again, we're extracting energy out of it, so even though we're dropping in pressure, the air would normally be slowing down, but because we're extracting the heat from it, we're rising our speed up again as it enters this right here. And then as it flows out of the exhaust, it's mostly constant temperature, constant speed, constant pressure. Um, this right here, we've extracted as much energy as we can out of this. So we're extracting energy in the form of heat at a relatively constant pressure and velocity. Relatively. All right, we want to keep the speed up because the speed of the air flowing across this is what spins it. It's not the pressure. It's not slamming into it. It's actually like a sail. So as the air flows around, actually, let's go to the next page and see. No, I don't think I have one. I don't. These turbine blades act more like a sail, or a wing, I guess is a better, it's an airfoil. So it's not catching the air, and the air is not pushing it to spin it. As the air flows across it, it creates a high pressure and a low pressure side, which sucks on it and spins it. All right, so we want that air to be going as fast as possible because that's how we extract the energy out of it. All right, we do have a little bit of residual thrust because you can see here that air is boogieing when it comes out of the back of that engine. So there's a very, very, very small amount of residual thrust that is created. All right. This just goes into a little more detail on the inside of the engine. We have our primary air that comes down here and feeds the fire. All right. The secondary air flows in all along here and dilutes that air. All right. And there you can see that primary air flowing through the inside of that stator. All right, so this is the engine fuel system. This comes up from the tanks. I gotta stop clicking. Fuel comes up from the tanks right here. It goes into the low pressure pump. This low pressure pump and the high pressure pump. Just kidding, where's my high pressure pump? High pressure pump. Okay. Low pressure pump right there and the high pressure pump are both driven off of that N1 gear train, off of the axial compressor. So as this spins, it slings fuel out into here, and then a portion of that fuel gets slung down through a tube inside of the main fuel line. All right, so the main fuel line has a smaller line inside of it. This fuel gets jetted through that right there. This is called an ejector. And the purpose of the ejector is a venturi. So as this relatively high pressure fuel, so this is a low pressure pump, but this fuel coming out of this is moving much faster than the fuel in this line, and the purpose for that is to shoot that fuel through that to suck the fuel up from the tank. So some helicopters use lift pumps in the tank to provide positive pressure. This engine does not need that because of this ejector right here. So some of that fuel comes off the low pressure pump and is rerouted back to the intake of the low pressure pump through the ejector to create a venturi and pull the fuel up. The other part of the fuel comes off the low pressure pump and comes right around here. And here we have the start purge valve. All right. This is internal to the pump and metering assembly, which is mounted on the front of the engine. All right. The start purge valve, the purpose of that is when we turn the prime pumps on at the beginning, this fuel comes up through here. It flows all through here. It fills all this up. And then when it gets to right here, if the stop electro valve is in the closed position, it piles up and it can't go anywhere. So then the start purge valve opens up and allows the fuel to return to tank. So this is what the prime pumps, this is what gives you your priming. So at shutdown, all this fuel drains back into the tank. So the next time you start your prime pumps up, it fills all these lines with fuel. And then once they're all full of fuel, and the stop electro valve right here keeps it from going any further, then it pushes back and goes back to tank. All right, so right here we have a oil fuel heat exchanger. This is in the oil filter, and the purpose of that is to use the fuel to cool down the oil. But more, there's separate oil coolers, but more importantly, it uses the oil to heat up the fuel so that you don't have to worry about ice forming in the fuel at high altitudes and really cold temperatures. And warmer fuel it atomizes better, which helps it to burn better. All right, on the intake side of your fuel filter, which is right here, on the intake side of the fuel filter, you have a fuel pressure transmitter. And then you have on the outlet side, you have a fuel pressure and temperature transmitter. And the computer system looks at these two pressure transmitters right here and determines whether or not your fuel filter is clogged. Depending on the difference between these two pressures, it can figure out how clogged this fuel filter is. And if it gets too clogged, it'll throw a light in the front, and then it'll also open up this ball valve so that the fuel can flow around the filter, because dirty fuel is certainly much better than no fuel. All right. Also, on the outside of the pump and metering assembly, you have this little blue button. It's not a little red button, it's a little blue button. It's a little blue button that pops out to let you know that you are in an impending bypass situation, meaning we have not reached enough pressure to open this valve, or maybe we have and just didn't catch it when this popped. But certainly this is letting us know that there is an impending situation where this has either intermittently opened up or is about to open up. So it gives us a little bit of a bellwether there. All right, so moving on down the line here, we're still low pressure. Now we are going to enter the high pressure side of the pump. This ramps the pressure up tremendously. And then we have a last chance filter right here. All right, this fuel filter and this assembly right here is actually somewhat external to it's mounted on the pump and metering assembly, but it's physically mounted on the outside. There's a bowl that is integrated with it. This is on the inside. You can get to it by removing a little plate, but this is your last chance. So we've already gone through the main filter. So anything has been filtered out. We got clean fuel going into this high pressure pump. But if this high pressure pump starts making metal, we need something to catch that. All right. And then we have a check valve right here that if the high pressure pump makes more fuel than the engine needs, which it'll constantly make more fuel than the engine needs, then that excess fuel is returned to the intake of the high pressure pump. All right. And then whatever is not used backs up and gets back to tank there. All right. If that is necessary, but it's usually not. This should shut down at about 15% N1. All right. So coming on down along the way, here we have our constant pressure valve. All right, so this valve right here is what maintains a constant pressure in the system. This is not a variable pressure system. Like say there's some I cannot some common rail fuel systems will, instead of on typical car engines, will alter the amount of fuel going into the combustion chamber by altering how long the injector is open, so that would be a constant pressure system. And then some of them alter it by varying the fuel pressure in the rail. All right, so this system keeps a constant pressure inside of here, and it does it by this constant delta pressure valve. All right, and returns whatever fuel goes over that required pressure back to the intake of the filter, which then routes it down to the intake of the high pressure pump. All right, so this fuel right here acts against this, the face of this, and then other fuel on the other side acts on the other face, so on the other side of your metering unit. So if it maintains that constant pressure on both sides of the metering unit. All right, so here we have our actual metering unit. This is what the computer controls in order to control the amount of fuel that gets to the engine. This is what controls our N1. All right, so this is controlled by two stepper motors on one needle, and then there's one unit that returns the position of this needle back to the digital electronic control unit. So as this needle opens up, more fuel flows through. As the needle closes, less fuel flows through, and everything is good. All right, we've got one additional check valve here so that during shutdown, the fuel, the pressure from the engine can't get pushed back into the engine here. And it helps to keep the, dang it, I did it again. It helps to keep the system primed after shutdown to make it a little bit easier for the system to prime itself on the next startup. All right, all of this takes place inside the pump and metering unit assembly. All right, as soon as the fuel leaves the pump and metering unit assembly, it goes through a optional fuel flow meter. So not all aircraft have that fuel flow meter. The Hype Performance 145 does, and it's shown on the dash that lets you know how much fuel each engine is using. So that takes place in between the pump and metering assembly and then the fuel valves assembly. This is mounted on the top of the engine, at the very top of the 12 o'clock position. Let's go back. It's going to be mounted about right here. All right, so inside of this we have our stop electro valve. The stop electro valve has two windings on it, one closed, one opened. All right, so it holds it positively in one location or the other. Right now it's shown in the closed position, which stops the fuel from being able to go any further. All right, over here we have the pressurizing valve. This valve keeps fuel from going into the main injection until the engine is at a certain speed, and then that speed causes the fuel pressure in this line to rise up and push this ball valve back, and then allows the main fuel to come in here and start going into the main injection. And then it also comes around here and pressurizes the backside of the stop purge valve, and we'll go over what that is a little bit later. All right, so right here we have a resistor or a restrictor. The purpose of this restrictor is so that as the pressure starts ramping up, it provides back pressure to open this ball valve. All right, down here we have our start electro valve. This right now is shown in the closed position, and that's why there's no fuel beyond this spot. This is what keeps fuel from going to the start injectors during priming and during when the engine's running. All right, so we have start injector purge valve. It's a 2-ball valve. Right now, this is shown in the engine running position because we have P3 air, if we remember, the P3 air we talked about coming out right there, that P3 air is being routed to here. The spring holds the ball in the closed position so that the air cannot continue up into the fuel system, and then that air ventilates the start injectors so that they don't coke on the end of it. It cleans them out, and then air constantly flows out of those start injectors for the entire rest of the flight. All right, and last but not least, we have the combustor chamber drain valve right here, and you'll see right there it is being held in the closed position because it's right here, which is, if we remember, the highest point of pressure in the engine. So the combustor drain valve is where any excess fuel that's not used by the engine after shutdown drips out of the combustion chamber, runs down the bottom of the engine, and flows out of the combustor drain valve. All right, but obviously we don't want fire blowing out of that or air blowing out of that during engine operation, so the air pressure pushes that closed and seals it off when the engine's in operation. All right, so I will go into engine stopped. We've got no fuel in the system. The stop purge valve is held closed by the spring. The stop electro valve is held in the stop position, and as soon as you turn on the battery, it energizes this winding to pull it and hold it in the closed position. The pressurizing valve is held closed by the spring. The start electro valve is held closed by the spring. The start injector purge valve, this side is held closed by the spring, and this side is held closed by gravity. All right, so we throw our switch to idle. We go from off to idle. All right, so we have prime pumps on, which means technically the fuel is already right here. All right, so we throw our switch to idle. This right here portion of the start electro valve is de-energized, and this portion is energized, opening that valve up and allowing fuel through into this entire valve assembly. That fuel flows down this pipe, hits this ball, and at this point there is not enough pressure to push this spring, because the only fuel pressure right here is from the prime pumps. Simultaneously, the starter generator starts spinning the N1, and these igniters right here start popping multiple times a second. You hear them tick, 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 very loud. All right, the fuel, when it hits this ball, it's a dead end, so it flows down around here, and now right here the start electro valve has been energized, which pushes this ball against that spring. This side of the start electro valve is not used on this engine. That is an additional tapping that is available, but it is not used on this engine. So this ball is pressed against the spring, releasing it from this seal. The fuel flows around the ball, comes down into here, meets this ball, which was held closed by the start injector purge valve spring. As the fuel piles up on it, it pushes it open, flows around. Now positive fuel pressure goes up against this ball valve right here. If this ball valve fails, this ball gets stuck in the open position, then at this point we have raw fuel getting pushed back through the P3 airline and getting dumped back through the P3 into the portion of the engine which is not supposed to have fuel in it. That's a bad thing. All right. So the fuel is going to hold that ball valve closed. Again, it's going to now pile up, and its only option is to go out through here to the start injectors. These start injectors are just like the fuel injectors that are in most helicopters. All right, these are going to be your conical spray that atomizes just like that, and then these are set up to spray exactly where these igniters are popping. So as that engine starts spinning and this fuel starts spraying, it lights it on fire. And then the N1 blows that fire back down through the path. As the engine accelerates and starts picking up speed at about 30% N1, your igniters turn off. So these stop popping. The fuel now has enough pressure to push this ball valve back. All right, fuel comes up here, surrounds this, and provides whatever pressure is here is now supplying the backside of that too, so that this fuel pressure cannot open this valve. All right, it continues on, goes through the main injection, and this is where you're going to hear that is when this main fuel starts kicking off. All right, when we hit 61% N1, the start electro valve de-energizes, which allows this spring to push this ball back against that seal, and then high pressure fuel additionally seats that ball against that valve. Simultaneously, the P3 air lifts this ball up out of this seat and allows the air to flow up through here. All right, when this valve closes and there's no more fuel pressure pushing on that ball, this spring pushes that ball and seals it. So now this air piles up inside of this chamber and has nowhere to go except to flow down this and starts ventilating your start injectors. All right. Now, at the end of the flight, when we're done and we want to shut down, we go to the off position. The stop electro valve de-energizes from the position that it's been in the whole time. It maintains current flowing through this throughout the flight. This should be red. So it maintains current on that throughout the flight to hold it in the open position. At shutdown, it de-energizes this and energizes this side, which pulls it closed. All right. At this point, the fuel or the engine is still spinning very fast. All right. It's probably, it was at idle speed. So whatever the engines needed to be in order to maintain that 78% NR. So when that slams shut, all that fuel piles up right here. You got that high pressure fuel piling up right there. That opens this valve right here, which that opens this valve. Oh, you schmuck. All right. Opens this valve, which immediately seals against the other side. But what that does is it opens this side of the ball valve, and all the fuel that was inside of this line supplying the P3 is now pushed back to drain this system right here. And that goes back. I guess they're not going to show it. That actually goes overboard into a can up under the engine. And then that can is pressurized during the next startup, and it blows it into the exhaust and burns it off so that it doesn't. Some helicopters, you'll see when they shut down, instead of pushing this into a can, they'll just dump it overboard. They'll dump it on the ground. So at engine shutdown, you'll see a lot of helicopters will just dump fuel directly on the ground. But Airbus is extremely environmentally conscious, and so they dump that fuel into a metal can at the that is mounted to the bottom of the engine, and then it blows that overboard. All right. Let me look at my notes here and see if there was anything else that I wanted to cover. I think that was pretty much it for now. There's probably going to be a number 2 on this because there's a lot of information that still needs to be covered on these engines, but this is the main portion of the mechanics of the engine. So you guys should have a pretty good idea how it works.